Okay. All right. So again, so we're gonna look at the evaluation of LV systolic function. And so some of the things that we're going to look at is, how you do your measurements. And as you can recall, we did some linear measurements. We talked about some volumetric measurements. Um, the volumetric measurements is mainly when we gonna do our ejection fraction. And you can do your volumetric measurement using 2D echo or 3D echo. It's always more accurate to use your 3D echo, but not, all labs have 3D echoes, so you have to know how to use your two dimensional echo. Also, we showed you how to do your ejection fraction, um, fractional shortening. We didn't look at global longitudinal strain. Uh, we we're not there as yet, so we didn't discuss that. Um, so let me just read this, probably two paragraphs here. So the quantification of cardiac chamber size and function is the cornerstone of cardiac imaging. So you have to know how to quantify what you're doing. Okay, with echocardiography being the most commonly used non-invasive modality because of its unique ability to provide real-time images of the beating heart, combined with its availability and portability. That it's, everybody have a echo machine, so you can get these studies done quite readily. The standardization of the methodology used to quantify cardiac chambers is maintained by creating and disseminating official recommendations. That's where the AAC comes in. Everything we teach in echo comes from the American Society of Echo. So you need to be familiar with the website and read the articles from the AAC. So recommendations for echocardiographic chamber quantification were last published in '05 by the American Society of Echo, and the European Association of Echocardiography renamed the European Association of Cardiovascular Imaging. That was the last, excluding this current recommendation. All right. So since then, echocardiography technology has continued evolving, with two major developments being real-time 3D echo. So in '05, we did not have the 3D echo. All right. And we also have myocardial deformation imaging. This is strain and strain rate and stuff like that. Later in the course, you will learn about things like that. So the goal of this document is to provide an update to the previously published guidelines, as well as recommendations and reference values, while eliminating minor discrepancies that existed between previous guidelines. So this is the current guidelines. The normal values in this update include 3D echo and myocardial deformation. As well, myocardial deformation is your strain rate, okay, uh, when possible. Importantly, compared with the previous guidelines, this update is based on considerably larger numbers of normal subjects compiled from multiple databases to improve the reliability of the reference values. So what they're saying that they use to compile to get this guideline, they use a much larger number of normal subjects. Although most Issues covered in this document reflect a broad consensus among the members of the writing group. One important issue the group debated was partition values for severity of abnormalities. Most often, in addition to describing a parameter as normal or abnormal reference values, clinical echo quantified the degree of abnormality in terms of mild, uh, moderately, and severely um, abnormal. All right, so these preambles are very important. So so severely abnormal. Um, so so basically, this is and we go over a lot of what they're saying in the subsequent paragraph. But this is the updated guideline. This is what you need to know. This is what you need to put in your pocket and walk around with. Okay. Um, all right. So when we do, let me make this a little bit larger. Okay. So I think this is large enough. So when we look at the LV, the left ventricle, okay, and we're gonna do measurement of the LV size. The most commonly used parameters to describe LV cavity size include linear internal dimensions and volumes. If you remember, when we did our parasternal long axis view, in diastole we measure the septal thickness, LV cavity size in diastole, and the posterior wall. These are very important measurements, and you need to know how to measure them properly. So measurements are commonly reported for end diastole and end systole. So in end diastole, the measurements that you need to have is your septal thickness, LV cavity size in diastole, posterior wall, and the aortic root. Those are the diastolic measurements. The systolic measurements, using the parasternal long axis, is your aortic root, sorry, not the aorta, the left ventricular flow tract diameter. So the LVOT diameter, the left atrial size or dimension, and the LV cavity size and systole. Those are your systolic dimensions, okay? Uh, so we can use those and derive global LV function. Remember, we have our linear measurements where we do fractional shortening. If we look at the apical four-chamber view, remember we plane the border and we get the diastolic dimension, and we also get the systolic dimension, and we use the formula ejection fraction is equal to the end diastolic dimension minus the end systolic dimension divided by the end diastolic dimension, and that gives you the ejection fraction. Okay, so those are all the things that you're going to use when you start doing your echoes to report uh, normal or abnormal values. To allow comparison among individuals with different body size, chamber measurements should be reported. Okay, so this is very important. There is a tendency now to index everything, and I think we'll briefly talk about that. And when we say you index everything, you divide whatever value you get by the body surface area. It is a more accurate description of what's going on because not everybody have the same size. Okay, people have different body size, body habitus. So to allow comparison among individuals with different body sizes, chamber measurements should be reported should be reported index to the body surface area. So what you're going to do, whatever value you get, you divide it by the body surface area, and that is a more accurate assessment of chamber size or chamber dimension. Then chamber dimension is a more accurate description. All right, so the linear measurements. So you need to know the difference between your linear measurements and your volumetric measurements. So the linear measurements, as we pointed out before, in your parasternal long axis view, in diastole, the values that you need, you're gonna get in diastole, septal thickening, LV cavity size in diastole, the posterior wall, and the aortic root. So it is recommended that linear internal measurements of the left ventricle and its walls be performed in the parasternal long axis view. Values should be carefully obtained perpendicular to the LV long axis. And when we actually looking at examples, I'll show you what the LV long axis is. Okay, so you should do your measurements perpendicular to the LV long axis and measured at or immediately below the level of the mitral valve leaflets, the mitral valve leaflet tips. So essentially, you're going to do your measurements at the mitral leaflet tips. Okay. In this regard, the electronic caliper, so your measuring tools, should be positioned on the interface between the myocardial wall and the cavity and the interface between the free wall and the pericardium. Essentially, when you measure your septal thickening, it should be from one side of the septum to the other side. You want the tissue blood plane. And then when you measure in the LV cavity dimension in diastole, it should be from the tissue blood plane. You want to exclude cords. You don't want to include cords in your measurements. So it is from the tissue blood plane to the tissue blood plane. Okay, and then you get your LV cavity size in diastole, and the posterior wall is where you have your tissue blood plane to the pericardium. Tissue blood plane just means from the blood to where the myocardial the wall is. Okay, um, and that's your two-dimensional measurements. Okay. We're not gonna, well, yeah, well, so when you're doing your M mode, we're not teaching M mode yet, but you need to have a little bit of idea what we mean by that. Okay, all right, so this is, okay, all right, so this is your M mode measurements, okay? So your two-dimensional echo is on top, your cursor is across the LV cavity, uh, the cursor first, well, the cursor show you the structures that the ultrasound beam is passing through. It passes through the chest wall, the RV wall, RV cavity, the ventricular septum, the LV cavity, the posterior wall, and the pericardium. So your M mode below, so your two-dimensional echo is on top, the M mode is below, and the M mode shows you the same structures that uh, that is in your two-dimensional echo on top. So the first thing you encounter is the chest wall. Then from the chest wall, you get to your chest wall includes, you know, your skin, subcutaneous tissue, fat, all that sort of stuff. Then you'll get to the pericardium. Then you get to the RV wall. Then the RV cavity is there. This is your septum, and the septum in diastole, the septum moves away from the posterior wall. This is the posterior wall below. This is the posterior wall. Okay, and there's this M mode gets there's a little bit of the mitral valve there, but we're not really concerned about the mitral valve. But anyway, in diastole, the septum moves away from the posterior wall, it is the largest dimension. So this is diastole, okay? And it usually corresponds to the onset of the QRS. So your EKG is always, should be always someplace close by. So your ECG is below. And the largest dimension usually is at the onset of the QRS. That's what we identify as diastole. So you can see you measure from one of the widest area to the widest area. Your systolic dimension now would be from the lowest portion of the septum, and if you come vertically downward from there to there, that would be your LV systolic dimension. So you just get the lowest point of the septum because the septum in systole, the septum moves towards the posterior wall. So the lowest portion of the septum, that's when it contracts fully in systole. Um, and then you just come down to the posterior wall because the posterior wall is going to move up because the heart contracts in systole. So this would be your uh, systolic dimension, diastolic dimension, okay? To measure the septum, you move from the top of the septum to the bottom, okay? And it's a diastolic measurement, okay? From the top to the bottom, okay? Septal thickness. Posterior wall, again, from your blood tissue plane to the pericardium, and you just measure that. These are all diastolic measurement. This is using M mode. We really don't use M mode for measurements. What we do, we use two-dimensional measurements, and that is what we've been teaching all along. So with your two-dimensional measurement, you're going to do measurements at the tip of the mitral leaflet. This is the tip of the mitral leaflet, and then diastole corresponds to the onset of the QRS. Okay, so from the tissue blood plane, okay, you want to exclude cords. You're going to come straight down to the tip of the mitral leaflet, okay, and that this is your left ventricle internal dimension diastole. Remember what we said, your this straight line should be perpendicular to the LV internal dimension. So this is your LV right there, and this is what the LV is. If you were drawing a line to represent the LV direction, it would be like this. So this line should be perpendicular to your the LV, the vertical, not the vertical, the axis of the LV long axis. So this line right here should be perpendicular. When we say perpendicular, it means 90 degrees to the LV long axis. So this line right here is represents the LV long axis. Essentially, this line is perpendicular to the walls. Okay. Sorry, it is parallel. Sorry about that. It's parallel to the walls of the LV, okay? Or it is parallel to the LV cavity, but it's perpendicular to this line that you you draw to measure the LV internal dimension in diastole. The tip of the mitral leaflet from the septum down to the posterior wall, perpendicular to the LV long axis, okay? And then you measure your septal thickness and your posterior wall thickness. All right, it's very important. All right. So it's very important that you know how to do your measurements. Okay. Incorrect measurements mean a faulty study. All right. All right, so that is our linear measurements. Okay, you have to know which measurements you're going to do in diastole and which measurements are done in systole. Now, the volumetric measurements, we do our volumetric measurements to get the ejection fraction. Because remember, the definition of ejection fraction is the left ventricular end diastolic volume minus the left ventricular end systolic volume divided by the left ventricular end diastolic volume. So it's a volumetric measurement. We use the modified Simpson rule or the method of disk. Okay, so LV volumes are measured using either two-dimensional echo or more recently three-dimensional echo. Volume calculations derived from linear measurements may be inaccurate because they rely on the assumption of a fixed geometric LV shape, such as a prolate ellipsoid, which does not apply in a variety of cardiac pathologies. Accordingly, the T-Coles and the quinone methods for calculating LV volumes from linear dimensions are no longer recommended for clinical use. So remember when I taught about the modified quinone method, said just for exam purposes, we do not use it in clinical practice. Okay, so volumetric measurements are usually based on tracing of the interface between the compacted myocardium and the LV cavity. So that, all right, so this is what we're saying. So with your two-dimensional echo, so we're just going to teach the two-dimensional echo. Three-dimensional echo is different sets of rules, but your apical, let's just use, you can use your apical 2 or your apical 4 chamber view, all right? So again, is your biplane method of disk or the modified Simpson rule. In diastole, okay? In diastole, when the heart is fully expanded, you're going to trace the endocardial border. You do not go around trabeculations and do funny things. You're tracing the endocardial border, okay? It should be a smooth, nice trace. Do not go around the chords, okay? So when you trace the border, the mitral valvular plane, it's a straight line. And then you're gonna, to get this length, what you do at the middle, at the midpoint, at the base, you drop a line straight up to the apex, and that's how you get this length. What the computer is doing, or what a computer does, is it divides the cavity into disc. It divides the cavity into very small disc, and it calculates the volume for the disc and then combine them. Mathematically, what it does, it calculates the volume for the disc and then integrate them. Okay, so it is the biplane method of disc, or you call it disc summation. Okay, so all you have to do is trace the endocardial border in diastole, and then in systole, you do the same thing. You trace the endocardial border. Do not include trabeculations and stuff in your tracing, and you come straight down, and the computer will, you can put a point right there and a point right there, and the computer will draw a straight line at the base of the heart. You need to find the midpoint at the base, and the apex of the heart, and then you get a straight line, okay? So your diastolic measurement and your systolic measurement. Volume measurements are usually based on tracings of the blood tissue interface in the apical 4 and 2 chamber views and the mitral valve level. The contour is closed by connecting the two opposite sections of the mitral ring with a straight line. LV length is defined as the distance between the middle of this line and the most distal point of the LV contour. Okay? And once you do this, the computer will give you the ejection fraction. Okay? You don't have to do anything else. It will give you the ejection fraction. We are not going to teach strain or strain rate at the present time. Now, you need to know the normal values for the stuff that you're doing, okay? And again, there's a tendency to index a lot of the things that you're doing. But this is you need to all right, let's go over this. So we're going to look at table 2 in a little detail. So table 2 shows the normal values for two-dimensional echocardiographic parameters of LV size and function according to the gender. So there's a push now to not give one set of values for everybody, but to give the values for males and the values for females. Okay? So because male and females tend to have different size hearts, so you have to give the values for both genders. While supplemental table 2 provides expanded data for the same parameters obtained from different echocardiographic views, and also includes the corresponding number of subjects used to obtain these data. Table 3 lists normal ranges and consensus based partition cutoffs for LV dimension. So essentially, what I'm going to show you now is the different values for the different sex, okay? And so we're not going to do 3D because 3D is a whole new set of measurements. So when reporting LV linear dimensions, the recommended method is 2D guided measurements. The LV size and volume measurement should be reported indexed to body surface area. So again, I said the tendency is to index most things. So for general reference, 2D echo LV end-diastolic volumes of 74 mLs per meter squared for men. So this is a normal value for males. Okay, you index it. So the volume that you get, you're going to divide it by the body surface area. So for the left ventricular end-diastolic volume, for males, it should be about 74 mLs per meter squared. And then for females, 61 mLs per meter squared. Okay. For the left ventricular end systolic volume, okay, for males, it should be about 31 mLs per meter squared. And for females, about 24. So again, we trying to index everything. That is divided by the body surface area. Again, we showed you how to do ejection fraction. It's just end diastolic volume minus end systolic volume divided by the end diastolic volume. And then the fractional shortening is when you use the linear dimensions. Okay. All right. So these are some of the. So this is what we're talking about. Um, so this is on the American Society of Echo website. So for 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 your linear dimension, okay, we didn't index the linear dimension. So for males, the range is about for diastolic dimension, linear dimension, LV dimension in diastole for males is about 42 to 58.4. Okay, that's LV dimension in diastole. For females, about 37.8 to about 52.2 LV dimension in diastole. Systolic dimension now, um, for males, it's about 25 to 39.8. And then for females, it's about 21.6 to 34.8. So you can see that there's a range. So, your left ventricle end diastolic dimension for males is a little bit larger than for females, but you have a range. And then if you're looking at just the volume, remember when we do our biplane method of disc or modified Simpson, we get our left ventricle end diastolic dimension. For male, it is about 62 to 150. The tendency now, however, is to index this. Okay, so but the absolute value ranges from about 62 to 150 mLs for males, and for females about 46 to 106. And then for the left ventricle end systolic volume, it's for males 21 to 61. These are mLs. And for females, a bit smaller, 14 to 42. There's a tendency to index these. That is, you're going to take the volume and divide it by the body surface area. Everybody has a body surface area. In order to get the body surface area of anybody, you need their height and their weight, and you have nomograms. These are tables that will convert the person's height and weight into an area. Okay, so for males, the left ventricle end diastolic volume index is 34 to 70, 34 to 74. For females, a little bit smaller, 29 to 61. And then you can also index the end systolic volume. You just get the volume and divide it by the body surface area. Okay, this is what is currently recommended by the AAC. And similarly, the ejection fraction is a new trend in ejection fraction, where ejection fraction, we don't just give one ejection fraction for everybody. Females gonna have a different ejection fraction, males gonna have a different ejection fraction. So if you look at the bottom of the table, okay, the ejection fraction of, let's see if this is the correct table. No, this is not the correct table. Let me get you the correct table. Um, so let me get you the correct table, and 1 second, let me get you the correct table. Yeah, so it's right out here. All right, so this is the ejection fraction, um, whether you're male or female, okay? And so you can see we have a normal range, a mildly abnormal range, moderately abnormal, and severely abnormal. Okay, so let's look at the male. So the ejection fraction is done the same way you always do ejection fraction, but The normal range for male is 52 to 72. Okay. It's mildly abnormal if it's 41 to 51. So below 52 is abnormal, but mildly abnormal 41 to 51, moderately abnormal 30 to 40, and then severely abnormal less than 30. I think we have been following this guidelines for quite some times, but you need to know the exact values. And then for females, the normal range for ejection fraction for females 54 to 74. Okay. uh, Mildly abnormal 41 to 53, and moderately abnormal 30 to 40, similar to male, and then severely abnormal less than 30. Okay, so these are the current guidelines for ejection fraction for the different sexes. All right, so I strongly recommend that you guys go on the American Society website and look it up. We exhaust the polar plot, and we you know you know tell you exactly what the polar plot stands for. The apex is right there, the mid cavity, and then the base. And we talk about the 16 segment model, the apical cap being the 17 segment. So you need to go over all these things. Um, we're gonna cap all of this by just looking at a brief male review. Let's do that. We haven't taught you guys this as yet, so we're gonna stop there. Um, but